what is the question? Okay. Uh, Rajuji was asking, longer pulse in transmon is equivalent to increasing theta further, even beyond 5. Please help me understand. I'm sorry for such a confusion creation. Okay. So, yeah, physicists, we physicists do these things a lot. Okay. Remember, yesterday's discussion, I did use the phi. Okay. Remember, we did use the phi as a label to represent the phase transition. Okay. Delta phi. And now again, I'm using phi for the angle representation. These two are two different topics, two different concepts, but same label is being used. So phi here is, this particular case, phi here is an angle. Okay. Phi is an angle here. There, phi is some kind of a phase transition is happening, that is represented by that. So both are two different things. We should not mix it up. Okay. So I'm sorry for that, such a confusion. Okay. I hope you understand now. There, the change in the phase is like becoming regular conductor to superconductor is actually conveyed by the delta phi as a change in the phases of the state of the system. Okay. So if the delta phi is very, very small, the system can easily become a superconductor. So that is what I meant there. Okay. Now the phi here is an angle which is used to represent a block sphere geometrically on a block sphere. Okay. Block vector or a quantum state. Okay then. So now I think your follow-up question also answered in that way. I mean pulse to drive the transmon. So the pulse again to answer, see in quantum states or quantum changes or quantum transition, every quantum state becoming from one form to other form. What I say is, if I have a quantum state psi, undergoes a change of unitary transition and becomes some psi prime. Initially, it probably pointing towards, let's say, some direction. Let me not go outside of a sphere. Initially, let's say it is psi 1. Later on, it becomes, let's say, psi 2. So what is happening is the vector is rotated about some axis from all the way from here to, okay, yeah, from here to here it is just rotated. Okay. So all that quantum operations are simply a rotation about some axis. So U is a simply rotation matrix. Okay, rotation matrix. It may not be a, in some cases, may not be a single matrix. It could be a combination of many matrices, rotational matrix. Suppose if I want to go from I vector to j vector, I can rotate by pi degrees, I to j, 9 by 2, sorry, pi by 90 degrees. Or I can do from I to k, 90. From k to j, I can come after 90. So it's a combination of two rotations. Okay. So all the quantum gates are about rotation only. Okay. Now, so yeah, that is the answer. And Bhaskaranji was asking question, does coherent source produces vertical and horizontal polarization together? If yes, how? Very good question. Okay, right? So horizontal vertical polarizations are what? They are polarizations of electromagnetic wave which is being in particular direction. The electric vector is being oscillating. See, if the electric vector is oscillating in, let's say, like vertical direction is, let's say v is, let's say I cap. Okay, let's say I cap x, and y is like this. Okay, this is a j cap. Now the magnetic field vector in fact oscillates in that y cap direction. Okay, now I cap and j cap are there, and the propagation is happening in the k cap direction. Okay, I hope I made a did I made a mistake? Yes, from I cap to j cap, if you curl a finger, you should get a j cap, k cap. So I should interchange. I'll just interchange. Okay, right. Now I have j cap here, I cap here. Now if I run my curling fingers from I cap to J cap, K cap should be given. So the electromagnetic wave is propagating in K direction, means that is Z direction. Okay. Now, so polarization of this electromagnetic wave now here is in electric field vector we usually address. So electric field vector polarization here in this case is it is oscillating in a J cap direction. So you can say that, or you can just simply give exponential, sorry, E small eta y. You can give polarization. Now, question, see, this electromagnetic wave is not just only wave, it's a collection of many photons. Each photon is representing electric field vector oscillating, and a bunch of, like, it's just a speck of energy, it's a burst of energy. Okay. Now, the coherent source may be emitting photons, of course, of all the possible polarizations. Okay, not only just horizontal and vertical, it may have many polarizations. So what I will do, I will use by using, okay, polarides, we can extract particular direction polarization, particular direction photons of, let's say, vertical polarization. Okay, so by default, if a laser is there, if a light is coming, so in that light, if I just say, it may have all the polarizations in it. Electric field vector, I'm just only drawing few. So all the vector polarizations is there. When I put a polaroid, means what I mean is polaroid usually comes with something called crystallographic axis. So it will have a crystallographic axis. Let's say crystallographic axis is of this one is vertical, as if it only allows a polarization parallel to its crystallographic axis. So the light which is coming is only having vertical polarization. Okay. Now what I will do, if I put for this vertical polarization light which is coming, if I put a crystallographic axis whose horizontal crystallographic axis is there, so then I will get zero light, because this horizontal crystallographic axis polaroid would not allow anything perpendicular to that. Okay. Now coming back to your question, yes, a given coherent light source may have not only vertical or horizontal, it may have all other polarizations also. What people do, if you just slightly tilt to 45 degrees the crystallographic axis, now what happens? Okay, let me show you that also. So let's say I have a polarization in all the directions. What I'll do, I'll take a crystallographic in such a way like it is angled to vertical. So here I will get, I'll also get this kind of polarization. I also get this kind of polarization. I also get this kind of polarization. Okay, right? So strictly saying, I should be getting only angular polarization. Okay, I should be getting only angular polarization. But you remember, even vertical polarization light has a component along the diagonal. Even horizontal also having a component along diagonal. So you can say the intensity wise there may be low, but this is angular ones will have more intensity. The other ones have a smaller intensity, like that, something like that. Okay, right? So by choosing what kind of a polaroid choosing polaroid, I can pick required polarization. That's what experimentalists do. Okay, right? So again, you are giving a nice explanation. Thank you. One more last query. In block sphere, one angular parameter indicates phase. Okay, very good. And phase difference between two, what are those two? Very good question again. So let me have that question and let me write down that explicitly. Okay, you see, you are right. This exponential I5 is there now. This is the one which is going to tell me whether 0 ket and 1 ket are in the same way they are behaving, relative phase wise. Phase means what? Phase means we usually say uh, they are in phase. Two people are in phase. They're thinking in phase. Okay. When it comes to 0 ket and 1 ket, what is the phase is? You can think electromagnetic wave or any given wave phase is, if I have a vector wave, see this is a wave. Okay. Let's say I have one more wave, slightly different. Let me have a different color. Okay. Let me draw it like this. You see now, at any given point, let's say you just take a situation. At any given point, you just take this wave is increasing. On the other hand, the second wave is actually decreasing in negative way. So they are like completely out of phase. Okay. So the first one is peaking at some point. Okay. Maximum positive value it took. Second one taking a maximum minimum value. Because they're completely out of phase. Okay. So even you can say they're 180 degrees out of phase. One guy is moving this way, another guy is going completely out of phase. The same way, the 0 ket and 1 ket, how well they're behaving the same is dictated by exponential I5. Okay. So when let's say phi value is 0, which implies exponential I5 is 1. So the relative, like the parity, they say sign of 0 ket and 1 ket is positive parity. So then I'll say 0 ket and 1 ket are relatively in phase. Okay, right? Let's say when phi is equal to pi degree radians. In that case, what happens? Exponential I phi is exponential I pi is equal to cos pi plus I into sin pi. By the way, sin pi is 0, cos pi is minus 1. What do I get? Quantum state is cos theta by 2, 0 ket minus sin theta by 2, 1 ket. So I have a relative negative phase between 0 and 1 with a minus sign. That is what they meant in the case of relative phase. So there, in the case, just to understand what is this relative phase is, a 0 ket is going in one direction, 1 ket is going in completely opposite direction. So that is what the relatively they are of opposite phase and they're of opposite parity. Okay. So that is what it meant, the phase difference between two, or what are those two? Yeah. Right. So you understand phase. See, one way of understanding phase is, if you just take electromagnetic wave, some amplitude, sine kx plus omega t, you know what is this electromagnetic wave? We already drawn that. See, this is electromagnetic wave, which is along k cap direction. Sorry, y direction it is oscillating. It is sinusoidal oscillation where kx by omega t is what? This is a phase angle. Okay, right? At a given point, whether the intensity should be a maximum or a minimum, either it is decreasing or it is increasing, is told by this phase angle. If I add some for phase angle, usually people do, they add some constant. Okay, they call it a phase constant. Okay, so here in this case, constant is 0. What I mean is whether to wave to start from 0 or it has to start from somewhere is actually told by this phase constant. Okay, that is something else. Now, so using that context, I'm sorry, using that context, we can understand what is the relative phase between 0 ket and 1 ket. Yeah, there are so many doubts. Constant phase difference. Okay, before that, what is a relation between mixed and pure state with this in context? Okay, yeah, yes. Okay, then. What is a pure system, mixed system? Probably I did discuss. I don't know whether I have done. So pure system is something, let's say I'll take 100 qubits. All of them are supposed to behave like a one quantum state like this. Okay. Roughly saying, let's say 40% in the ground, 60% in the excited. That is supposed to be a combination of given quantum states. All of them should behave like that. But because of the surrounding environment, what happens, they mismatch. Let's say there is a group which is having 39% and 61%, very close to the given quantum state but slightly deviated. So likewise, there are groups like say psi1, psi2, and psi3. Even though I have chosen same like sodium atom kind of a thing, so there is a combination of psi1, psi2, and psi3. So this is actually called a mixed quantum system or a mixed quantum state. Okay. Now, I can't represent this by simple quantum systems because there are so many of them for me. So what I'll do, I'll bring in something called a density matrix representation. What is this density matrix representation is, you take a given quantum state, take its outer product, you will be generating a matrix. So that they will call a density matrix. Why it is called density matrix is, I can write the overall density matrix of this entire system as rho total is equal to, let's say, if I close my eyes, pick an atom from a particular this 100 atoms, so there is a chance that is falling into the quantum state psi1. Okay. Similarly, there is a probability for quantum state psi n. So this will be written as I taking from 0 to n. So there will be a quantum outer product. I'm sorry. So this is outer product. Okay. So the mixed quantum state is represented using like this, pi rho I. So this is a mixed system. It is not a pure anymore because it's a mixture of many. So if psi1, psi2 all are equal, it becomes a pure system. So that is the difference between pure and mixed systems. So that it doesn't have a connection to this scenario. Like if I had to connect, what I will connect is, like I gave an example. It's a current source, like spill, like ejecting a set of photons. So all the photons are of like kind of photons. In the optics, definitely we can have all the photons behaving alike. So I can get a pure system. When I test whether the photons have got disturbed by surrounding environment, I can just check for in a time of let's say 1 minute how many photons I measure. From those measurement I can find out the ejected photons are a mixed system or a pure quantum system photons are not. Okay, right? Yeah, constant phase difference means the given vectors having a fixed phase difference of the given waves having a fixed phase difference as they go from any distance. So from a laser source, if see a laser, if there is a wave which is ejecting, another wave which is ejecting, you see at any point the difference between their peaks is remaining constant. So that is what happens in the case of lasers. Okay, so the difference between their peaks separation, like when they will peak, both the waves would remain the same. So that is a fixed path difference or fixed phase difference. It happens only in the case of lasers. That is what I explained, I think, yesterday. Okay, right. There are no two different things, but you are showing kit 0 and kit 1 as two entities moving, rather single electron photon moving. So phase difference between the two. Okay. So again, the way you see is the 0 and 1 are the two different states electron can exist in. Okay. There are two different states electron can exist in. Okay, so electron is common but the states are different. It is just like if inside your house, let's say it's a duplex house, you can go from ground floor to top floor and top floor to ground floor. Let's say something you are not finding, so you go back and forth to search for it. So likewise electron is going back and forth. Okay, so the ground state has some kind of a parity, upper state having a parity. How it is different? Let's say in the summer the top floor is having hot, ground floor is cooler, so there is a parity difference. Okay, in the normal time during the monsoon or somewhere, the temperatures may be more or less the same. Okay, so that is what between 0 and 1 I can have outer opposite parity, so that is a relative parity. So that is what comes in the quantum computing. Okay, right? So yeah, in the electron or photon, again, the same story. A vertical polarization, horizontal polarization in case of photon. Okay. So which state we can measure or observe? and prove how they are related. Yeah, we are coming to that. So we are losing a lot of time, so I have to hurry. Okay. So where did we stop here is we want to create a tool out of the basis vectors which we have here. So in the case of classical two-dimensional space, we are multiplying the unit vector to the given vector to find the component of x and y. So here in the quantum measurements, you can create a tool which is called projection operators. What they do is they project given quantum state into a particular either 0 ket or 1 ket. So basically, how do I create? Remember one thing, the quantum gate measurements are rotation matrices. It's like a matrix. So if at all, if there is a projection operator which allows me to do a measurement, it has to be a matrix. So now I have a computational basis 0 and 1. From the computational basis, I can create a projection operator. How? I take a projection operator. Okay, so just to have, yeah, P, yeah, okay, let me maintain a difference between probability and so projection operator capital P naught is actually outer product between 0 to 0, and projection operator 1 is 1 ket to 1 ket. These are the ones which help me to find out given quantum system is existing in 0 or 1. How do I know? I take the projection operator, multiply it onto the quantum system on the either side. Okay. So if it permitted, I take a like photons, some several hundred photons. On each photon, I make an operation of polarization operator, sorry, projection operator P naught. So what do I get here? On the left hand side, I have a alpha star 0 ket plus beta star 1 ket. Okay. On the middle, I have 0 ket and 0 outer product. Okay. On the right, I have alpha 0 plus beta 1. You see now? Now you see inner product between 0 to 0 ket is 1. Inner product between 0 to 1 is 0. So what I'll have from the right, I have only one term coming, which is alpha. Okay. From this term, I'll only get alpha. From the left, what I'll get? From left, I will get, okay, alpha star. Inner product between 0 to 0 is 1. Inner product between 0 to 1 is 0. So basically what I'm getting? Alpha star absolute square. So what is this quantity? It is the probability of system finding in the 0. Okay. Now, take a projection operator. You are making observation of the projection operator on the given quantum system. Once I am getting alpha square means I will do the projection operator measurement several times on the quantum system. I'll get the probability roughly something like 40% or 60 or something. Okay. Similarly, what is the P1 measured on the quantum system is, okay, so this is going to give me absolute beta square, okay, which is probability to find the system in state 1. So the first one is probability to find the system in state 0. Now the question you can ask me, what is happening to the system? Okay, right? When I make a measurement, what is happening to the system? I'll tell you how do you find mathematically. Instead of making measurement on the either side, making multiplying on the other side, what you do? Take the projection operator, multiply only on one side. So what you will get? Okay, just a minute. 0, outer 0, alpha 0 plus beta 1. You see now? Inner product between 0 to 0 is 1. So alpha 0 ket only I'll get. So inner product between 0 to 1 is 0. So I'll getting quantum state. Now I'm getting after making a measurement, what is the state it is left into 0 ket. Okay, right? So this is how on paper it is showed. When it comes to measurement, what is happening is the system was forced to fall into classical form of 0 ket and 1 ket, depending on the chance I am, like the way I created. Let's say I created 40 like quantum state to exist in ground for 40% times, exited state in 60% of the time. In that case, when I do the same experiment several times, I see ground 40, excited 60. Okay, so now, like I said earlier, without disturbing the state, how do I find? So I have bunch of photons coming, measuring is fine because photons are coming one after the other. But when it comes to materials, okay, I can't have a cloned qubits, all the qubits, okay? And let's say I have a transmon, let's say qubit, which is realized on IBM circuit. So there the transmon is there, it is in superposition. So how do I find it is combination of its ground and excited is between 40 and 60? How do I know? I would be using something called the readout photon. I did mention like a readout qubit, which will go slightly near to this actual qubit, okay, slightly near, and extract the information to some extent. Since that extraction is not exactly the same, exactly right, so what I do such several iterations, and I'll take the statistical sum, and from there I figure out what is absolute alpha square, what is absolute beta square. That is how the measurement is done. That is what called weak measurements in quantum systems. Okay, so let me jump to the PPT. Okay, and to build the required background, I did spend nearly 1 hour 45 minutes. Okay, weak continuous measurement. So I have a Schrodinger cat expression as a Schrodinger cat figure, where what you see is a Schrodinger equation explicitly mentioned as a time derivative, where E is converted into IH cross dou by dou t operator form, but Hamiltonian retained as it is as a matrix. Okay, right? Fine. Now coming back to internal, you see a measurement operator. How do I measure? Using a projection operator. So earlier, I know that the projection is, or the quantum state is defined on 0 ket and 1 ket computational basis. My corresponding projection operators are 0 outer 0, P1 is 1 outer 1. So here, let's say given quantum state is defined on, okay, some set of quantum X states, okay, where X can generalized to 0, X can take 0 and 1. Remember, X can take any other value. So if I have only 2 data points, I just need 1 qubit. Let's say I have 4 data points. What I will do now, I will just 2 qubits and club them and create a state of substates 0 0 0 1 1 0 1 1. Remember, now this is a basis. Now if X belongs to this basis means X can take value 0 0 0 1 1 0 1 1. Remember that. In that case, what are the projection operators? Projection operators will be 0 0 outer 0 0 0 1 1 outer 1 1. There are other three. If you want, I can write down. Okay. Okay, see, this is how, depending on the dimension of the quantum state, you see the dimension of the quantum state here is 4 dimension, dimension of the quantum state is 2 dimension, 2D. So depending on that, I can create a projection operators. So the moment you do the projection measurement on a given quantum state, what do I get? I get absolute square values. So in this above case, if the quantum state is having alpha 0 plus beta 1, what do I am getting? I am getting absolute alpha squares, absolute beta squares I am getting. Let's say in a 4-dimensional case, I will be getting absolute alpha 0 0 whole square and alpha 1 1 whole square. All these individual values I will be getting. If I perform the experiment several times, like strong measurement is, I don't worry about whether system fall into particular state or not. I don't worry. I just do a brutally a measurement on that without bothering about it is falling into one of the classical form. You know why? We have seen that P naught acting on psi forces the system to falling onto zero state. Okay, right? And if you use P now P1 on the quantum state, it forces the system to fall to one state. Okay, right? So that is a strong measurement for you. You are not minding and go head on collision with the qubit and get the essence of the qubit. Okay, so to get the full essence, I have to take the same qubit like 100 times, several hundred times. I have to perform the experiment and get the exact information, provided I have availability of all such qubits. Okay, if not, I can only do the same thing in the photonics case. Okay, so the weak measurement is something like I said earlier. I'll have a very test qubit. We go very close, and I will get the statistical sum of the information that may be wrong individually. To just like exclude all the wrong information, I'll put all the observation results together and I will get the weak measurement done. And where, okay, so there is a chance the measurement is done with for example photonics case, some kind of a detector. I might see some kind of a fringes there, means intensity of varying. So what are the operators? I again the same kind of operators I'll have, projection operators. Okay, and here you do see a wave nature and particle nature. This cartoon just says that. So basically, the output of this measurement you can still get quantum state intact, whether it is in the representation in terms of position or represent of in terms of linear momentum. They just showed here. So sometimes when I make a measurement, system goes from one format to other format, means one representation to other representation. What is that is, if the quantum state is represented, remember, okay, what I mean there is, the quantum state is defined on 0 ket and 1 ket. If I use a projection operators like a plus ket, outer plus ket, minus, minus. So if I wrongly see this is defined on 0 and 1, I use a wrong projection operator like measuring a blood pressure using a thermometer. Okay, so P plus acting on psi gives you a projection onto plus ket and minus ket states. Okay, so that is inconclusive result we will get, but we'll still get plus ket and minus ket with some weights. So I'll get some plus ket and I'll get some minus ket. Okay, so because of that, what happens, I may end up in wrong conclusion. So that is what mentioned here. So change from projection position to momentum and so on, plus ket to minus ket, the basis change. So that is what mentioned. Okay, so next let's go. The strong projective measurement and a weak projective measurement, and I do continuous weak measurements to just satisfy my weak observations. Okay, so what is the description? As I said earlier, most importantly the effects you see here. Maximal disturbance would create with a strong projective measurement, minimum disturbance with one single measurement, but only thing we'll see possibly a partial collapse in the system may happen because of partial disturbance. If you do several of such thing, information and disturbance both accumulate gradually, but we may get extract the information of the given qubit to a greater extent. Okay, so there's a basic formalism is given here. So the moment you have a collection of many qubits, you start observing them. Probably you are just creating some mixedness in the system. So you are disturbing the system. How the overall system is being disturbed, how do I find? So I need to find out the dense, where is the dense of qubits which were disturbed, which group has disturbed, all those things you do a density matrix formalism and you find. So you can also represent how the density matrix changing in time. So basically dou rho by dou t, or it's a regular derivative. Let me use the regular derivative just to avoid the confusion. D rho by dt in fact is equal to minus I by h cross h into rho. Okay, so other terms are there, you don't worry about that term. Let's understand what is this term. What is this term is, in the rectangular bracket, what you have is called a commutator bracket. Okay. What is this is? Let's say I have a matrix A and B. Commutator between A and B is AB minus BA. As we know, commutating matrix multiplication is anti-commutator. Commutator doesn't satisfy. AB is not equal to BA. So here the rate of change of quantum system because of the environment is actually connected to Hamiltonian. As we know, you get back to the notes, you see, okay, a quantum system going change from psi to psi prime means there is a unitary which is acting on psi, giving a psi prime for us. Basically, what is the unitary? Unitary is a matrix which is capturing the information of the Hamiltonian around the system. Okay, the system energy around. So unitary operator is a exponential minus ih t by h cross. This is a unitary operator. Now, as you can see, the quantum state is represented by like this. But since I have a mixed quantum systems, so let me write down the density matrix formalism. Okay, psi prime would be psi outer, and rho is psi outer psi. Now, what is this first quantity? First quantity is u psi u dagger. Okay, so which is u into, okay, let me write down in terms of psi. U is u into rho dagger. Now you see, this is a quantum evolution. Quantum evolution means either side of density matrix, you multiply u dagger, you get a new quantum system. Now, how this new quantum system is changing, how do I find? Very simple. Take this row, you retain the u as it is, okay, right? You retain it u as it is. Now, I want to find rate of change of this, okay? Now, see, as you can see, there is a temporal dependence on u and there is a temporal dependence on psi also, okay? So what you can do is, okay, so let me keep it as u rho. Yeah, I think let me differentiate individually. So what I'll do, can create a two terms. In the first case, I'll have the first one coming as this u dagger plus, okay, d by dt u into psi, okay, psi into u dagger. Okay. Now, when you differentiate this quantity, what do you get? You will be getting dt. Say u means what? Minus ih cross, na? Minus ih cross by t. So I'll be getting, when I differentiate, what do I get? Okay, let me remove that. Minus ih cross. Okay. Right. With respect to time, let's say everything is constant. Minus ih by h cross into psi into u dagger. Plus, here also I'll get a 1 minus sign. Okay, this time it is a dagger, so I'll get a minus of minus, so it will be a plus sign. Okay, u into psi u dagger. Okay, now what I'll do, okay, so let me write down h cross h, okay, u dagger h cross u into rho into u dagger. So carefully, if you can see u into u dagger, you can show, you can take a common of I h, okay, I by h here. you'll get h rho minus rho h. Okay. So basically what you can show is the rate of, I maybe made a mistake of getting of u. So wait, what you will get is I h, okay, h by h. What I'm getting here is uh, 1 by I by h cross h rho minus rho h, which is commutator of h into rho. This is what I will be getting. So there is small mistake here. I think I'll send you notes for that. So somewhere the u will disappear. Okay, let me use my notes here. So you will be getting the rate of change of the system in terms of commutator bracket. So other terms what you see here, these are the terms which are actually captured from the environmental interaction. They're introducing some kind of a dephasing, a decoherence. All those things are actually directly multiplied. So for a simple system, these things may not be existing. Okay. So basically what I mean is the rate of change of the system is written by stochastic master equation, which is addressing how densely the system is varying. Okay, right? So basically if I'm doing a weak measurement, I'll get a information from the system in terms of some signal, classical signal, which is like a Gaussian signal like this. From there only I have to extract the information of the system. So the signal is having some Gaussian noise, so that is actually captured here. Okay, right? So quantum trajectories and conditional evolution, when you make the system measurement, it will be evolving. So that is what I meant there. So the most important, what is the physical realization of quant qubits and how are you going to do the measurements? Okay, so superconducting qubits, what you showed here, what I showed you is these things. And cavity QED systems are inside a cavity I can have photons which can act like a qubit for me. And there is a way you can have a confine the few electrons within three-dimensional space, which is actually going to have a quantum dots. And optomechanical systems, there are some mechanical system which responds to which to the light. So those are optomechanical systems. In that way we can create a qubits and start measuring them using the technique of weak measurement, where we'll get the essence of the information of the qubit in terms of the signal. From there only we can make the what this qubit is made up of, what is its ground state, what is it excited state, and so on. Okay, so I have one more PPT for you also, since we did not have a time, we did not go through, but anyway I'll upload to the Google Drive. You can go through it. Okay, yeah. I'll just conclude in 5 minutes. uh, so this is error disturbance relation in quantum measurement. Basically, if you recollect Heisenberg uncertainty principle, I think I have it somewhere here. You see? Okay, where is that? Yeah, I think this is the Heisenberg uncertainty principle. Okay, you may not be seen in this format. Okay, let me write down what is it. Okay, 1 minute. Okay, I need to edit that. Huh? Okay, 1 minute. Yeah, 1 minute. Okay, so in quantum systems, I can never exactly measure position and momentum accurately. I always make a mistake. That mistakes are always going to have a product value greater than h cross by 2 Planck's constant. Okay, so basically what I mean is I'll take a tool A, I'll take a tool B operator. A gives me position, B gives me momentum. So the error in calculating a position is delta A, error in calculating delta B. So both together product is going to be greater than h cut by 2. So there is a way to get that value exactly. Okay. So so there is a relation between these errors, okay, to the measurements. Okay, So errors and the disturbance which is we are going to create through measurement, that kind of a connection you can also derive from the quantum mechanics or quantum principles. So this PPT talks about the relation between the errors and the measurement. Okay. So this is the generalization. There is a inequality. Okay. So I have an expression for you. Finally, I'll conclude by showing that. Okay, so basically there are several relations derived by many people, Eisenberg, Joawa. Okay, so I think this is repeated, and Brain's yard. Okay, so these are actually several ways, and the one which is showed is one of a kind. Okay, so the measurement relation to the error. Okay, where is the? I do have some expression somewhere. So what I can give you is I can share your notes, okay, where you would be able to show error in position, error in momentum is exactly greater than h by 2, where delta A and delta B correspond to this uncertainties, which is going to be h by 2. Okay, so remember A is a position operator, B is momentum operator. Okay, so from there you can derive. I'll send you a notes, you can go through it probably tomorrow, looking at the or looking at the schedule. Just a minute. So tomorrow we will be touching upon quantum measurements, standard quantum limits, quantum non-demolition measurements. Probably these two topics would connect to whatever we discussed today, so in that way we can conclude tomorrow. Okay, right? So let's see the questions. There's so many questions popping up. Uh, right. I just stopped at. Yeah, there is a question at 5:36. Which states we can measure or observe, and how they are related? So basically, you can measure any quantum states. Only thing is you are brutally measuring and disturbing that entire state or not. If you don't want, you have to do a weak measurements, and from the several weak measurement, you have to get the essence. Okay, right. So there is a how to differentiate weak and strong measurements. So the differentiation is very simple. So the probing technology or probing mechanism is not indulging with the state of the system, means it's a weak measurement. In that case, you can't make. So I'll just tell you a simple analogy. Okay, somebody is standing very far to you. Okay, so some serious afternoon is there, sunlight is coming. What you do, you make a several observations to make out who is that. Okay, if he's very close, you just make one single observation and figure out who is that. So likewise, you are observing the quantum state from very far with a several weak observations. By that way, you are not disturbing the system. Okay, right? Yeah. Particle or wave behavior of a quantum. That depends, right? Situation you're talking about. The photons can behave like a particle as a wave. Electrons can behave as a particle as a wave. Okay. So depending on the scenario, they change their behavior. It as if they have flexibility, right? So the experiment which I'm performing, depending on that, I can perform interference experiment even with the electrons, even though they are particles, they show wave nature when they performed with the experimental setup of interference. Okay, right? So it has nothing connection wise to here. So it's just a generalized answer for you. When Veeramanikyamji, how external disturbance parameters and quantum states with the Kelvin temperature related to weak and strong measurements? Is it relevant question to this? Yeah, it is relevant. See, you meant to not to disturb the quantum qubit and go with a probe which is only slightly disturbed. While creating a small probe, you are creating a chance for environment to come into picture and disturb the system. So, right, so the small hole which you are creating to see inside a qubit, which is there inside a box, would also allow some light to come from outside, na? So that environment is always there. So that is what we have to address. What is the extra factors of errors which are coming, which is being addressed even in this PPT somewhere. Okay, remember, yes, the environment has a role to play with some errors creeping in from that end. So we need to even address that and you do the measurement analysis. Okay, yes, is a relevant question here. Can you differentiate on observables versus measurement? Okay, so I'll just conclude with that question. I think, remember, in quantum mechanics, okay, if I want to find the position, I have a, let's say I have want to point the position, I can create a position operator. It's a observable. If I want to find a momentum, linear momentum, I will have a momentum operator p hat. If I want to find energy, energy hat. Okay, if I want to find a let's say angular momentum, I have angular momentum operator. Okay, that are the operators or observables. The name is being used either way, they're referring to the same thing. But you are asking about the observables to the measure difference. So when I make a measurement on the system, let's say I take a quantum momentum operator, act on a quantum system, which push the quantum state to, let's say, some new quantum states IP with some probability value of PA. So here you see the measurement is pushing the quantum system to go to some other form with some probability. And with what probability we saw that is a measurement result. Okay, right? So measurement operators, how are they constructed? From the basis elements itself I can construct. The system is defined on a basis elements of x, so the measurement operators are constructed as a outer product with the x with x itself. Okay, so please don't confuse with the momentum operator to any generic operator. Let me take a generic operator. Okay, right? I'm sorry. Fine. So yeah, that is the answer for your question. So there are plenty of questions there in this session. Okay, thank you for that. So it's better to clarify than going ahead with a very, very complicated science. See, if you just go through the second PPT, it has so much of more concrete and complex things. So there is no point in I'm just blabbering on this without clarifying the doubts which were there being asked by the participants. Thank you very much for those things. I hope I clarified. If not, don't worry. We have several days we'll be following with you, so we can clarify along the way. Right? Yeah. Yeah. Thank you so much. So I'll hand it over to Visti sir. Sir, please
Thank,
take.
thank you, sir, for your time and this informative talk. Maybe I can say some introductory because we are now starting more and more this uh, quantum science or quantum physics. So, being a Sunday, I know it's like thank you all the participants and particularly speakers for me agreeing to have the talk today and attending because this schedule have so many holidays and we planned like we could finish it before Diwali break. So I thank all the participants for joining on this Sunday. So this way we are coming to the end of 6 day and today we are posting the quiz and tomorrow will be the last date. So I request all the participants to please finish it well in time so that it does not need to be like extend further and we will close by tomorrow. So once again thank you speaker for the session, Aswat sir and Dr. Jaskaran for today, and thank you all for joining. Once again thank you and see you tomorrow.
Yeah. Thank you, sir.
Thank you, sir.